So for part B of the problem, we have to show that for small x, the net force is proportional to x cubed. And we also have to figure out what the potential energy is as a function of x to the 4, and what the constant in front of that term is going to be. So here we have part B of the problem. And we're assuming that x is very small or much, much less than L naught. So this means that x over L naught is going to be much, much smaller than 1, which means that we can use the binomial approximation for the term in this parentheses. So recall that for 1 plus epsilon all to the n, that is going to be approximately equal to 1 plus n epsilon for n times epsilon much, much less than 1. Which means for small x, force on the bead, we'll call f of x, because it's a function of x, that's going to be equal to negative 2kx times 1 minus, and let's use the binomial approximation, so this is going to be approximately equal to negative 2kx times 1 minus, and in brackets, 1 minus x squared over 2 L naught squared. We're just multiply the term by n, which in this case is negative 1/2. So now notice that the ones cancel, and negative over negative will give you a positive, so you get that's going to be equal to negative 2 times kx times, in brackets, x squared over 2 L naught squared, which is going to simplify to negative kx cubed over L naught squared. So here we've shown that for small x, or x much, much less than L naught, the net force on the bead is going to be a function of x cubed. Now to figure out the potential energy, we're going to have to use our formula for the potential energy stored in a string, since all of the potential energy of the bead is going to be the potential energy in the two springs due to their stretching. So recall that the potential energy in a spring is going to be given by, let's write it over here, U of S. Potential energy in one of the springs is going to be half of k times delta L squared, where delta L is the stretch of the spring from its equilibrium position. So the total potential energy of the spring as a function of x is going to be 2 times the potential energy in the springs, since there are 2 springs, which is just k times delta L squared, where delta L is L minus L naught. So let's expand these terms, which will give us k times, in brackets, L squared minus 2 L naught. Let's write it as L naught L plus L naught squared. And if we substitute in our values for L, we're going to get k times L naught squared plus x squared, which is just the L squared term here, which gets rid of the square root, minus 2 times L naught times the square root of L naught squared plus x squared plus L L naught squared. So now let's factor out a factor of L naught squared from the square root and group like terms. So that's going to give us k times, in brackets, 2 L naught squared plus x squared minus 2 L naught squared times square root of 1 plus x squared over L naught squared. And we can go even further by factoring out a factor of L naught squared. So I'll save time and just write it out without explaining each term. So that's going to give us 2 plus this. That's 2 times this. Alright. So now, this may not look like a function of x to the 4, but since we're dealing with small x, let's write out the Taylor expansion of the term in the square root. So we have that, let's write it over here. So we have that the square root of 1 plus x squared over L naught squared, using our rules for Taylor expansion, that's going to be approximately equal to 1 plus x squared over 2 L naught squared minus x squared, or x to the 4, over 8 L naught to the 4. And we're going to ignore the higher order terms since they quickly disappear because x over L naught is much, much less than 1. So x over L naught to the nth power is going to quickly disappear for higher orders of n. So with this approximation, we're going to plug that in to our formula for the potential energy, which means that U of x is going to be equal to k times L naught squared times 2 plus x squared over L naught squared minus 2 times, in brackets, we have 1 plus x squared over 2 L naught squared minus x to the 4 over 8 L naught to the 4, which, if we expand it out, is going to give us k times L naught squared. And we have 2 plus x squared over L naught squared minus 2 minus x squared over L naught squared plus x to the 4 over 4 L naught to the 4. So notice that the 2's cancel out and the x squared over L naught squared cancels out, leaving us with just this positive term right here. So finally, if you write it out, we have k L naught squared times, in brackets, x to the 4 over 4 L naught to the 4, which is going to give us our final answer of k times x to the 4 over 4 L naught squared. So that's going to be our final answer for the potential energy of the bead as a function of x for small x. So if we write out the potential energy in the form of c times x to the 4, and here we have shown that c is just going to be equal to k over 4 times L naught squared.